What was the Big Bang? Before matter, before stars, before any of the structures that fill the night sky, the universe did not exist. Not in any form we would recognize. No space to move through, no time to count. And then, in a fraction of a moment so small, it defies all intuition, everything began. A cosmos of unimaginable heat and density burst into existence, and from the single instant, a journey of nearly 14 billion years began. One that would eventually produce atoms, stars, worlds, and minds capable of asking why any of it happened at all. This is the story of the Big Bang. But what exactly was it? Was it an explosion? Was it a beginning? Was it the only beginning? Scientists have spent more than a century piecing together the answer, and what they have found is stranger, grander, and more beautiful than anyone first imagined. They found galaxies fleeing from each other across the void. They discovered an ancient whisper of radiation echoing from the universe's infancy. They traced the lightest atoms back to a cosmic forge that burned for only a few minutes in the universe's first chapter. Before we begin, let us know where in the world you are watching from and what time it is for you right now. Drop it in the comments below and settle in, because this is one of the greatest stories ever told. The expanding universe, a discovery that changed everything. The story of how we came to understand the Big Bang begins not in a laboratory, but under the open sky, with astronomers pointing telescopes at faint smudges of light scattered across the darkness. In the early years of the 20th century, the dominant view among scientists was that the universe was eternal and essentially unchanging. The Milky Way was thought to be the entirety of creation, an island of stars adrift in infinite, featureless emptiness. The universe simply was, and had always been, and always would be. That comfortable picture began to crack almost immediately when Albert Einstein published his theory of general relativity in 1915. General relativity reshaped humanity's understanding of gravity in the most fundamental way possible. Gravity, Einstein showed, was not a force pulling objects toward each other across empty space, as Newton had described it. It was instead a curvature in the very fabric of space-time itself, caused by the presence of mass and energy. The more massive an object, the more it bent the surrounding geometry of space and time, and other objects simply followed those curves. When mathematicians began applying Einstein's equations to the universe as a whole, they discovered something deeply unsettling. The universe, according to those equations, could not sit still. It had to be either expanding or contracting. A perfectly static cosmos was mathematically unstable, like a ball balanced on a knife's edge. Einstein himself found this result so philosophically troubling that he introduced an extra term into his equations, a kind of repulsive constant, purely to force the mathematics to produce a static universe. He would later call this decision the greatest blunder of his career. Meanwhile, an American astronomer named Vesto Slipher was making a puzzling series of observations at the Lowell Observatory in Arizona. He had been studying the spectra of distant spiral nebulae, objects that most scientists still believed were simply gas clouds within the Milky Way. When Slipher broke their light apart into its component colors, he noticed something remarkable. The characteristic spectral lines, the fingerprints of specific chemical elements, were shifted toward the red end of the spectrum in nearly every case. This redshift, as it was known, indicated that these objects were moving away from Earth at tremendous speeds, some of them faster than anything ever recorded. Slipher did not fully understand what he was looking at. The puzzle deepened when Edwin Hubble, working with a powerful new telescope at Mount Wilson Observatory in California, resolved individual stars within some of these spiral nebulae. Among them were a particular type of variable star called Cepheid variables, which pulsed with a brightness that directly revealed their true luminosity. By comparing how bright they appeared with how bright they actually were, Hubble calculated their distances. The answer stunned the scientific community. These were not gas clouds inside the Milky Way. They were entire galaxies, each containing billions of stars, separated from us by distances of millions of light years. Hubble then combined his distance measurements with Slipher's velocity data and discovered a relationship that would transform cosmology forever. The further away a galaxy was, the faster it was moving away from us. This was not a coincidence or a local effect. It was a universal pattern. Every galaxy in every direction was receding, and the most distant ones were receding fastest of all. This relationship, now called Hubble's law, had one inescapable implication. The universe was expanding. To understand what this means, think of a loaf of raisin bread rising in an oven. As the dough expands, every raisin moves away from every other raisin. No single raisin is at the center of the expansion. The dough itself is growing, carrying the raisins along with it. The universe behaves in the same way. Galaxies are not moving through space like rockets. The space between them is stretching, carrying the galaxies along like markings on a balloon being inflated. And if space is expanding now, then running the film of cosmic history backward must lead to a time when everything was far closer together, compressed into a smaller and smaller volume, growing hotter and denser as it condensed. Taken to its logical extreme, this backward extrapolation leads to a single moment when all the matter and energy in the observable universe was squeezed into an unimaginably small, hot, dense state. That moment is what we call the Big Bang, what the Big Bang was, and what it was not. The name Big Bang was never meant to be flattering. It was coined in 1949 by the British astronomer Fred Hoyle during a radio broadcast, and Hoyle used it with deliberate mockery. He was a champion of a rival theory known as the steady-state model, which proposed that the universe had no beginning or end. New matter, he argued, was continuously created to fill the gaps left by expansion, keeping the cosmos eternally young and unchanging. Hoyle found the idea of a universe born from a single hot, dense event absurd, and his sarcastic label was designed to ridicule it. Instead, the name stuck, traveled around the world, and became the most recognized phrase in all of cosmology. The irony was complete, but the phrase carries with it a deeply misleading image that is worth correcting from the start. The Big Bang was not an explosion in the way we normally imagine explosions. When a bomb detonates, hot material blasts outward through pre-existing space. There is a center, a surrounding void, and fragments flying away from that center. The Big Bang was nothing like this. The Big Bang was not an explosion in space. It was an expansion of space. There was no pre-existing void into which matter erupted. Space itself came into being, and it was everywhere at once. There was no center of the explosion, no edge from which debris flew outward. Every point in the universe was, in a very real sense, the center, because the universe encompassed all points simultaneously from the very first instant. The standard Big Bang theory does not attempt to describe what caused this expansion or what, if anything, existed before it. It is not a theory of creation in the philosophical sense. It is a rigorous, evidence-based description of how the universe evolved from an extremely hot, dense, and compact state into everything we see today. It describes the physics of the first fractions of a second, the formation of the first atomic nuclei, the release of the first light, the birth of the first stars and galaxies, and the large-scale architecture of the cosmos we inhabit. The question of what triggered the Big Bang, or whether there was a time before it, lies at the edge of current scientific understanding, and we will explore it. But first, we must understand the extraordinary evidence that makes the Big Bang theory one of the most rigorously tested frameworks in the history of science. The ancient light that confirmed everything of all the evidence supporting the Big Bang, one discovery stands apart for the sheer drama of how it was made. In the years following Hubble's confirmation of the expanding universe, a small group of theoretical physicists began working out the detailed physics of what a hot, dense, early universe would have looked like. George Gamow, a brilliant and flamboyant physicist with a gift for making complex ideas vivid, collaborated with two younger colleagues, Ralph Alpher and Robert Herman, to develop a mathematical model of the universe's earliest conditions. Their calculations led them to a striking prediction. If the early universe had been hot enough and dense enough for nuclear reactions to occur in its first few minutes, then it must also have been filled with an extraordinary amount of thermal radiation. As the universe expanded over billions of years, this radiation would cool and stretch, shifting from visible light into microwave wavelengths. By the time it reached the present era, it should pervade all of space uniformly, arriving equally from every direction, carrying a temperature of just a few degrees above absolute zero. In 1948, Alpher and Herman published this prediction. It was precise, quantitative, and testable, and for more than a decade, almost nobody paid attention to it. The confirmation came not through a deliberate search, but through one of science's most celebrated accidents. In 1964, two radio engineers named Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in New Jersey, calibrating a large horn-shaped antenna originally designed for satellite communications. Their goal was to eliminate all sources of unwanted noise from their receiver so they could make precise astronomical measurements. No matter what they did, they could not get rid of a faint, persistent hiss. It came equally from all directions. It did not vary with the time of day, the season of the year, or the pointing direction of the antenna. They checked everything. They inspected every component of the antenna. They evicted a pair of pigeons that had nested inside the horn and carefully removed the evidence of their habitation. The hiss remained. At roughly the same moment, a team at Princeton University, led by Robert Dick, had independently rediscovered Gamow's prediction and was actively building a detector to search for exactly this signal. When Penzias and Wilson learned through a mutual acquaintance what the Princeton group was doing, the pieces fell into place instantly. The persistent hiss was the cosmic microwave background radiation, the ancient afterglow of the Big Bang itself, the oldest light in the universe. The two Bell Labs engineers had stumbled across a fossil of the universe's infancy while trying to remove what they assumed was interference. They received the Nobel Prize in Physics in 1978. The cosmic microwave background, or CMB, tells us an extraordinary story. For the first 380,000 years after the Big Bang, the universe was so hot that ordinary atoms could not exist. Instead, the cosmos was a plasma of free protons, neutrons, and electrons, through which photons could barely travel before being deflected by a charged particle. Light was perpetually trapped, scattered in every direction almost as soon as it was emitted. The universe was opaque, like a fog so thick that no beam of light could penetrate it. Then, as the universe continued to expand and cool, something remarkable happened. The temperature dropped to roughly 3,000 degrees Kelvin, the temperature of a dim red star. At this threshold, electrons slowed down enough to be captured by atomic nuclei, forming the first stable neutral atoms. With electrons no longer roaming freely, they were no longer available to scatter photons. The universe became transparent. Light, for the first time, could travel freely across cosmic distances. The photons released at this moment of clearing have been traveling ever since. Over 13.8 billion years of cosmic expansion, they have been stretched and cooled until their wavelengths fall in the microwave portion of the electromagnetic spectrum. They now arrive at our detectors from every direction in the sky with a temperature of 2.725 Kelvin, just barely above absolute zero. This is the CMB, a snapshot of the universe at 380,000 years old, the earliest direct image we will ever have of the cosmos. What makes the CMB so scientifically powerful is not just its existence, but its details. The radiation is extraordinarily uniform across the sky, varying in temperature by only about 1 part in 100,000. This uniformity confirms that the early universe was remarkably smooth and homogeneous, consistent with the Big Bang's description of a hot, uniform initial state. But the tiny variations, the faint ripples in temperature that required the most sensitive instruments in history to detect, are equally important. These minuscule fluctuations were the seeds of everything that would come later. Over billions of years, gravity amplified these slight density differences, pulling matter together into the galaxies, clusters, and vast cosmic structures we observe today. Without those tiny ripples, the universe would be a featureless sea of gas, and none of us would be here to wonder about it. The first 3 minutes. A universe forged in fire. The CMB gives us a view of the universe at 380,000 years of age. But the Big Bang Theory makes detailed, testable predictions about far earlier moments, right down to the first few minutes of cosmic history, when conditions were so extreme that the universe operated as a vast nuclear reactor. When the universe was only a few seconds old, it had cooled from the unimaginable temperatures of its first instance to a temperature of roughly 10 billion degrees Kelvin. That is still far hotter than the core of the most massive stars. The universe at this point was a seething, rapidly expanding plasma of protons, neutrons, electrons, positrons, photons, and neutrinos. Protons and neutrons were constantly interconverting, transforming back and forth through weak nuclear interactions. As the universe cooled, this interconversion slowed, and a stable ratio emerged. For every 7 protons, there was approximately 1 neutron. This ratio would prove crucial. The nuclear reactions that forged the first light elements could not begin immediately. Deuterium, which is the essential first step in building heavier nuclei, consists of one proton and one neutron bound together. In the extreme heat of the earliest moments, any deuterium nucleus that formed was instantly shattered by high-energy photons before it could combine further. This is known as the deuterium bottleneck, and it held back the assembly of complex nuclei until the universe had cooled sufficiently. When the universe was approximately 3 minutes and 46 seconds old, the temperature had dropped below about 900 million degrees Kelvin, and deuterium nuclei could finally survive long enough to fuse further. What followed was a brief but furious burst of nuclear activity. Deuterium nuclei combined with protons and neutrons to form helium-3, which in turn fused into helium-4. The helium-4 nucleus, with its 2 protons and 2 neutrons, is exceptionally stable, and the reactions during this period were extremely efficient at producing it. Given the roughly 7-to-1 ratio of protons to neutrons, the arithmetic worked out to produce a universe that was approximately 75% hydrogen and 25% helium by mass when the nuclear reactions finally ceased around 20 minutes after the Big Bang. Trace amounts of deuterium, helium-3, and lithium-7 were also produced. The universe was too hot for only the briefest window, and the conditions were never right for building heavier elements like carbon or oxygen. Those would have to wait for the first stars. This process is called Big Bang nucleosynthesis, and it makes one of the most precise and testable predictions in all of cosmology. The theory specifies not just that hydrogen and helium should be the dominant elements, but the exact proportions in which they should appear, along with the trace amounts of the other light elements. Decades of astronomical observations have confirmed these predictions with remarkable precision. When astronomers study the oldest, most chemically pristine regions of the universe, distant gas clouds illuminated by ancient quasars, or the outermost envelopes of the oldest stars, they consistently find hydrogen and helium in proportions that align almost perfectly with what Big Bang nucleosynthesis predicts. The deuterium abundance measured in remote ancient gas clouds is a particularly sensitive test, as deuterium is easily destroyed in stellar interiors, and so its current abundance reflects its primordial concentration. Observation and theory agree. This is not a small thing. The Big Bang theory was making specific, numerical predictions about the chemical composition of the universe, and the universe turned out to match those predictions. This is science at its finest, a theory generating testable forecasts that can be checked against nature, and nature consistently returning the right answer. The first fractions of a second, before atoms, before nuclei. The first 3 minutes produced the universe's light elements. But what happened in the moments before that? What was the state of the cosmos in the first fractions of a second, when conditions were so extreme that even protons and neutrons had not yet formed? This is where physics enters its most speculative but also most fascinating territory. Our understanding becomes less certain as we push closer to the beginning, but the framework provided by the Standard Model of Particle Physics, the most thoroughly tested theory in the history of science, allows us to trace the universe backward to conditions that existed when it was only millionths of a second old. In the first microsecond after the Big Bang, the universe was so hot that quarks, the fundamental building blocks of protons and neutrons, existed as free particles rather than being confined inside larger structures. The cosmos was filled with a quark-gluon plasma, a soup of quarks and the force-carrying particles called gluons, moving freely in a state that has been recreated in miniature form by powerful particle accelerators like the Large Hadron Collider at CERN. At roughly 1 microsecond after the Big Bang, the universe had cooled enough for the strong nuclear force to confine these free quarks into the composite particles we call hadrons. Protons and neutrons were born. For every proton and neutron that formed, there was also an antiproton and an antineutron. When matter and antimatter particles meet, they annihilate each other, converting all their mass into pure energy. If the early universe had produced exactly equal amounts of matter and antimatter, they would have canceled each other out completely, leaving behind nothing but radiation. The universe would be a cold, dark sea of photons with no atoms, no stars, no galaxies, no life. But something subtly asymmetric happened in those first instants. For every billion antiparticles produced, there were roughly 1,000,000,001 particles. This seemingly negligible imbalance was everything. As matter and antimatter annihilated each other in the cosmic holocaust of the first second, this tiny surplus of matter survived. Every atom in your body, every star in the sky, every galaxy in the observable universe is descended from that 1 in a billion excess. The physical process that caused this asymmetry, called baryogenesis, is still one of the deepest unsolved problems in physics, but its fingerprints are written across all of existence. By the time the universe was 1 second old, the particle-antiparticle annihilation was largely complete. The residual matter, protons, neutrons, electrons, and their accompanying neutrinos, was all that remained. The universe had settled into the simpler but still extraordinary configuration that would give rise, minutes later, to the first nuclei. Going further back, into the first trillionths and quadrillionths of a second, the 4 fundamental forces of nature converge. Today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force behave as distinct and separate entities. But at the temperatures that existed in the universe's first moments, theoretical physics suggests they were unified. The electromagnetic force and the weak nuclear force merge at energies accessible to our most powerful accelerators, forming the electroweak force, a unification confirmed in the 1980s by the discovery of particles called W and Z bosons. At still higher energies, corresponding to times perhaps a trillionth of a second after the Big Bang, the strong nuclear force may also have united with the electroweak force in what physicists call grand unification. And at the very first conceivable instant, the Planck time of about 10 to the power of -43 seconds, gravity itself would have merged with the other forces in a fully unified theory of everything. This is the era we understand least. At the Planck scale, both quantum mechanics and general relativity are simultaneously relevant, and neither theory alone is sufficient to describe what was happening. A complete theory of quantum gravity remains one of the greatest open challenges in theoretical physics. Inflation, the universe's moment of sudden madness. Even as the Big Bang theory accumulated spectacular successes, cosmologists noticed several features of the universe that were puzzling. The cosmos appeared to be extremely flat, meaning its geometry was Euclidean rather than curved like a sphere or a saddle. The cosmic microwave background was almost perfectly uniform in temperature across the entire sky, including regions so far apart that in the standard Big Bang model, they could never have exchanged heat or information. And the expected abundance of exotic relics from the earliest moments, such as magnetic monopoles, was nowhere to be found. These were not minor inconsistencies. They required extraordinary precision in the universe's initial conditions, a degree of fine-tuning that cried out for an explanation. In 1980, the physicist Alan Guth proposed a solution that was radical even by cosmological standards. He suggested that the very early universe had undergone an extraordinarily brief period of exponential expansion, far more rapid than the gradual expansion we observe today. He called it cosmic inflation. The inflationary expansion is thought to have begun around 10 to the power of negative 36 seconds after the Big Bang, and to have ended by roughly 10 to the power of negative 32 seconds. This means it lasted for less than a trillionth of a trillionth of a trillionth of a second. In that almost incomprehensibly brief interval, the universe is believed to have expanded by a factor of at least 10 to the power of 26, and possibly far more. A region of space smaller than a proton was stretched to a size larger than a grapefruit, and perhaps much larger still. This expansion was driven by a hypothetical energy field called the inflaton field, which possessed the unusual property of generating a kind of repulsive gravity, pushing space apart at an accelerating rate. When the inflaton field eventually decayed, its energy was deposited into the universe as a blast of hot, dense matter and radiation, igniting the standard Big Bang expansion. The elegance of inflation is that it resolves all three puzzles simultaneously. The flatness problem dissolves because any initial curvature in space is stretched so dramatically by inflation that the observable universe looks flat, just as a small patch on the surface of an enormous balloon looks flat, even though the balloon itself is curved. The horizon problem disappears because all the regions of the observable universe that appear to be out of causal contact with each other actually originated from a single tiny patch of space that was in thermal equilibrium before inflation stretched it to cosmic scales. They were in contact. Inflation separated them. And the absence of magnetic monopoles is explained by the fact that the inflationary expansion diluted their density to essentially zero across the observable universe. Beyond solving these puzzles, inflation also provides a mechanism for the origin of cosmic structure. During the inflationary expansion, the universe was dominated by the inflaton field, which obeyed quantum mechanical laws. Quantum mechanics is inherently uncertain, and those uncertainties produce tiny random fluctuations in the energy density of the inflaton field across different regions of space. Inflation then stretched these microscopic quantum jitters to macroscopic scales, imprinting them as slight variations in density across the early universe. These density variations are precisely what we see as the temperature fluctuations in the cosmic microwave background. Regions that were slightly denser attracted more matter over time, eventually collapsing under gravity to form galaxies, clusters, and the vast cosmic web. The statistical pattern of temperature fluctuations in the CMB, measured with astonishing precision by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, matches the predictions of inflationary models with striking accuracy. The seeds of every galaxy in the observable universe trace back to quantum uncertainties magnified by inflation in the universe's first moments. Inflation is not yet proven in the way that the basic Big Bang framework is proven. The nature of the inflaton field remains unknown, and different versions of inflation make different detailed predictions. But its ability to explain so many otherwise puzzling features of the universe has made it an essential component of the standard cosmological model. The dark architecture, matter we cannot see. By the time the universe was a few 100,000 years old, the immediate drama of particle creation, antimatter annihilation, and nucleosynthesis had passed. The universe had settled into a vast, gently expanding sea of hydrogen and helium gas, uniformly warm, gradually cooling. This era is called the Dark Ages, because there were no stars yet to illuminate the cosmos. The CMB photons that had just been released were the only light traversing this dark expanse. For hundreds of millions of years, no photons in the visible spectrum traveled between any 2 points in the universe. If you could have been placed inside the cosmos at this moment, you would have seen nothing. Absolute, total, universal darkness. Yet this darkness was not static. It was pregnant with potential, vibrating with the slow gravitational dynamics that would eventually crack open into blazing light. The neutral hydrogen gas that permeated the universe was not perfectly smooth. It retained those tiny density variations seeded by quantum fluctuations during inflation, frozen into the structure of the CMB and inherited by the matter that decoupled from radiation at recombination. These were subtle ripples, temperature differences of only 1 part in 100,000, density contrasts barely detectable even with the most sensitive modern instruments. But gravity is infinitely patient. Over tens of millions of years, it steadily amplified these small differences. Slightly denser regions attracted surrounding gas, growing denser still. Slightly underdense regions lost matter to their neighbors, growing emptier. The universe began the long, slow process of developing structure. But within this apparent stillness, invisible forces were already at work, sculpting the universe's future far more powerfully than the ordinary matter alone could manage. Those forces were the gravitational influence of dark matter. Dark matter is one of the most extraordinary discoveries in the history of physics, and also one of the most frustrating. Because decades after its existence was established beyond reasonable doubt, we still do not know what it actually is. It does not emit light. It does not absorb light. It interacts with ordinary matter only through gravity. It is, in every sense of the phrase, invisible. The evidence for dark matter is overwhelming and comes from multiple independent directions. Galaxies rotate at speeds that cannot be explained by the gravity of their visible stars and gas alone. Without additional unseen mass, the outer regions of galaxies would fly apart. Galaxy clusters bend the light of background objects through gravitational lensing far more powerfully than their visible mass would allow. The large-scale structure of the universe, the way galaxies are distributed in clusters, filaments, and vast empty voids, cannot be reproduced in computer simulations unless dark matter is included as the dominant form of mass. And the precise pattern of fluctuations in the CMB is perfectly consistent with a universe in which dark matter makes up roughly 27% of the total energy content, compared to only about 5% for ordinary atomic matter. Dark matter does not interact with the electromagnetic force that governs how light and ordinary matter behave, which means it was not impeded by the radiation pressure that slowed the clumping of ordinary matter in the early universe. While the hot plasma of protons and electrons was held back by the constant pressure of photons, dark matter was free to clump under its own gravity from early on. It began accumulating into vast, invisible halos long before the first atoms formed. When recombination finally occurred and the universe became transparent, ordinary matter was suddenly free from the radiation pressure that had been holding it up. It flowed into the waiting gravitational wells of the dark matter halos, concentrating in their centers. This was the beginning of cosmic structure formation. The dark matter provided the scaffolding. The ordinary matter filled it in. Over hundreds of millions of years, the gas within these halos continued to cool and condense. In the densest concentrations, the pressure and temperature at the center eventually climbed high enough to ignite nuclear fusion, and the first stars were born. These first stars, known to astronomers as population 3 stars, were unlike anything that has formed since. The primordial gas contained only hydrogen, helium, and traces of lithium. Without heavier elements to act as efficient coolants, the gas clouds had to accumulate far more mass before they could collapse sufficiently to form stars. Theoretical models suggest that the first stars were colossally massive, many times larger than the heaviest stars forming today, some perhaps hundreds of times the mass of our Sun. Such enormous stars burned through their fuel at a ferocious rate, living for only a few million years before dying in spectacular supernova explosions. These ancient supernovae were the universe's first cosmic factories for heavy elements. Inside the cores of these short-lived giants, nuclear fusion had built carbon, oxygen, nitrogen, silicon, iron, and the entire periodic table of heavier elements up to iron. The explosions scattered these newly forged atoms into the surrounding gas. This chemical enrichment was among the most consequential events in cosmic history. The elements created in those first stellar explosions became the ingredients for subsequent generations of stars, and eventually for planets, oceans, atmospheres, and living organisms. Every carbon atom in your DNA was forged inside a star. Every oxygen atom in every breath was scattered into space by a stellar explosion. The universe's chemistry began with hydrogen and helium, and the rest was built by stars, the birth of galaxies, and the web of the cosmos. As the first stars enriched the gas around them with heavy elements and their ultraviolet light ionized the surrounding hydrogen, the universe entered a new phase of complexity. Small concentrations of gas, dark matter, and young stars began merging and growing under the relentless pull of gravity. Galaxies were being born. Galaxy formation, like so many things in the universe's history, was hierarchical. It did not happen from the top down, with enormous galaxies forming all at once. It happened from the bottom up, with small structures forming first and then merging over time into larger and larger assemblies. The earliest galaxies were nothing like the majestic spirals and ellipticals we see in deep telescope images today. They were small, irregular, chaotic collections of stars and gas, forming rapidly, colliding with neighboring proto-galaxies, sparking furious bursts of star formation wherever gas was compressed by an impact. Billions of years of such mergers gradually built the more organized, larger structures that populate the present-day universe. The Hubble Space Telescope, and more recently, the James Webb Space Telescope with its infrared sensitivity, have allowed astronomers to directly observe this process. When these instruments peer at the most distant reaches of the observable universe, they are looking back in time to when the universe was only a small fraction of its current age. The galaxies they find there are indeed smaller, more irregular, and more actively star-forming than the galaxies nearby. The further back we look, the more the universe resembles the bottom-up assembly process that theory predicts. On the largest scales, the distribution of galaxies follows a pattern called the cosmic web, one of the most visually striking structures in all of nature. Galaxies are not distributed randomly through space. They cluster along vast filaments, thread-like concentrations of matter hundreds of millions of light-years long. Where filaments intersect, the densest clusters of galaxies gather. Between the filaments lie immense voids, regions of near emptiness that stretch for hundreds of millions of light-years in every direction. This architecture, which has been mapped by large galaxy surveys over recent decades, matches with extraordinary fidelity the patterns predicted by cosmological simulations based on the Big Bang model with dark matter and dark energy. When astronomers run computer models that begin with the initial conditions revealed by the CMB and allow gravity to act over 13.8 billion years, the virtual universe they produce looks strikingly like the one we actually inhabit. This agreement is one of the most powerful validations of the Big Bang framework as a whole. Dark energy. The universe's accelerating expansion. For most of the 20th century, cosmologists assumed that the expansion of the universe was gradually slowing down. After all, gravity was acting across all of space, and its pull should have been steadily decelerating the outward motion of galaxies. The question was not whether it was slowing, but by how much, and whether it would slow enough to eventually halt the expansion and pull the universe back into a big crunch. Then, in 1998, two independent teams of astronomers studying a particular type of supernova made an announcement that sent a shockwave through the scientific world. These supernovae, used as standard candles to measure cosmic distances, were fainter than expected. They were further away than they should have been if the universe's expansion were slowing. The data pointed to only one conclusion. The expansion of the universe was not slowing down, it was speeding up. The discovery earned the leaders of both teams the Nobel Prize in Physics in 2011, and it introduced a new and deeply mysterious ingredient into the cosmological model. This acceleration is attributed to a mysterious entity called dark energy, a form of energy associated with empty space itself that exerts a repulsive gravitational effect, pushing space apart. Rather than diminishing as the universe expands, the energy density of dark energy remains constant. As space grows larger, there is more of it, and so the repulsive effect grows. Gravity, which was dominant when the universe was young and dense, is slowly being overwhelmed. Dark energy is estimated to make up approximately 68% of the total energy content of the universe, making it by far the dominant component of cosmic reality. Ordinary matter makes up only about 5%. Dark matter contributes roughly 27%, and the nature of the remaining 68% is one of the deepest unsolved mysteries in science. Theoretical physicists have attempted to explain dark energy as the energy of the quantum vacuum, the ceaseless fluctuations of empty space predicted by quantum field theory. But when they calculate what this vacuum energy should be, they arrive at a value roughly 10 to the power of 120 times larger than what is actually observed. This mismatch, perhaps the largest discrepancy between theory and observation in the history of physics, is known as the cosmological constant problem, and it remains unresolved. The discovery of dark energy transformed our picture of the universe's future. Rather than eventually halting and perhaps reversing into a big crunch, the universe appears destined to expand forever, accelerating as it does so. Galaxies will gradually retreat beyond our observational horizon. The cosmic web will thin out. In the extraordinarily remote future, the observable universe will be a cold, dark, nearly empty place, with only the faintest memory of the richness it once contained. This fate was set in motion by the Big Bang, encoded in the initial conditions of the cosmos, as surely as a thrown ball's trajectory is encoded in the force and angle of the throw. The singularity problem, the edge of what we know. There's a point in the Big Bang story where our best scientific tools fail us completely. Trace the expansion of the universe backward in time, apply the equations of general relativity, and you arrive inevitably at a mathematical catastrophe. As the universe is compressed to smaller and smaller sizes, its temperature and density climb toward infinity. At the very beginning, all of space, all of matter, all of energy was concentrated in a state of infinite density. This is the initial singularity, and it is not a physical description of reality. It is a mathematical warning sign. When a theory predicts an infinity, it is telling you that it is being applied in a regime where it no longer works. General relativity is a classical theory. It describes the large-scale behavior of gravity and space-time with extraordinary precision, but it does not incorporate quantum mechanics, the framework that governs the behavior of matter and energy at the smallest scales. The singularity lies at the intersection of these two incompatible theories. To understand what was actually happening at the first instant of the Big Bang, we need a theory that can describe gravity quantumly, a theory of quantum gravity. No such theory has yet been confirmed experimentally, though several candidates have been proposed. String theory suggests that the fundamental entities in nature are not point-like particles, but tiny vibrating strings of energy. At the Planck scale, where the singularity would otherwise arise, strings would smooth out the infinite densities into finite, extreme, but manageable conditions. In some versions of string theory, the Big Bang might not be an absolute beginning, but a transition from a previous state, perhaps the collision of higher dimensional structures called branes. In these scenarios, two enormous membrane-like structures existed in a higher dimensional space, slowly drifting toward each other before colliding with enormous force. The energy released in that collision would manifest as the hot, dense conditions of the Big Bang. Before our Big Bang, on this picture, there was a prior universe, or at least a prior physical state, operating by different rules in a higher dimensional landscape. Loop quantum gravity takes a different approach, proposing that space-time itself is not a smooth, continuous fabric, but is granular at the smallest scales, woven from discrete loops of quantum geometry. In this framework, there's a minimum possible unit of volume. Density cannot actually become infinite, because there is a floor below which space cannot be compressed. As the universe is traced backward to smaller and smaller sizes, it reaches a state of maximum but finite density, at which point quantum gravity effects generate a powerful repulsive force that causes the universe to rebound. This is the hypothesis known as the Big Bounce. The Big Bounce is one of the most intriguing alternatives to the standard Big Bang singularity. It suggests that our universe did not begin from nothing but emerged from the collapse of a previous universe. That previous universe contracted under gravity, reached its maximum compression, and then rebounded into the expansion we call the Big Bang. In this picture, time did not begin at the Big Bang. It has existed continuously through the bounce, though in a state of extraordinary compression and transformation. If the Big Bounce is correct, then asking what came before the Big Bang has a straightforward answer. There was a previous universe, contracting toward the event that would become our beginning. And before that, perhaps, another universe, in an endless or very ancient cycle of cosmic rebirth. Each cycle is not a perfect repetition of the last. The conditions at each bounce, the distribution of matter, the values of certain physical parameters, might differ from cycle to cycle, producing a succession of universes each subtly different from its predecessor. Whether this sequence extends backward infinitely or began at some first cycle that genuinely had no antecedent is a question that current physics cannot answer. Was there a time before time? The concept of a time before the Big Bang forces us to confront one of the most disorienting ideas in all of cosmology. If time itself was created at the Big Bang, along with space and matter and energy, then the question of what came before becomes as meaningless as asking what is north of the North Pole. You can keep walking north until you reach the pole, but at the pole, the concept of north ceases to have any meaning. Similarly, if time began at the singularity, then asking about before is asking about a direction that does not exist. This perspective was articulated powerfully by the physicist Stephen Hawking, who also contributed, along with Roger Penrose, the mathematical theorems that demonstrated the inevitability of the singularity within general relativity. Assuming that theory remains valid, Hawking suggested a model called the no-boundary proposal, in which the universe has no beginning in the same way that a sphere has no edge. Time near the Big Bang, in this proposal, behaves more like a spatial dimension, and the universe simply closes on itself in a way that makes the question of a prior state dissolve rather than demand an answer. But this remains speculative. The no-boundary proposal, like the Big Bounce and colliding brain models, is a theoretical framework whose full implications are still being worked out. None of these theories has yet produced predictions that can be tested with current instruments. What is clear is that the singularity represents the boundary of current physics. Everything before it, if there is anything, lies in territory that can only be reached with a theory we do not yet have. This is not a failure of science, but a frontier of it, one of the most exciting in the entire landscape of human inquiry. The universe from quantum nothing. Among the most provocative ideas in modern cosmology is the suggestion that the universe did not emerge from a pre-existing state at all, but arose spontaneously from the quantum vacuum as a kind of enormous quantum fluctuation. The quantum vacuum is not empty in the classical sense. According to quantum mechanics, Even regions of space that contain no matter are populated by ceaseless fluctuations in the energy of quantum fields. Pairs of particles and antiparticles spontaneously emerge from these fluctuations, exist for incredibly brief moments, and then annihilate and disappear. This incessant activity is not a theoretical abstraction. It has measurable consequences, including the Casimir effect, in which two closely spaced metal plates are pushed together by the imbalance of vacuum fluctuations inside and outside the gap between them, and the Lamb shift, a tiny but precisely measured shift in the energy levels of hydrogen atoms caused by the interaction of the electron with virtual photons from the vacuum. The key insight that makes a universe from nothing scenario potentially viable involves the total energy of the universe. General relativity allows for the possibility that the positive energy of all the matter and radiation in the universe is precisely balanced by the negative gravitational potential energy stored in the gravitational field. If these two contributions cancel out exactly, the total energy of the universe would be zero. A universe with zero total energy could arise as a quantum fluctuation without violating conservation of energy, because on balance, nothing was created. The physicist Edward Tryon first proposed this idea in 1973, and it was later developed by others, including Hawking, and more recently, the physicist Lawrence Krauss, whose writing on the topic sparked a lively public debate about what it means for something to arise from nothing. The critical additional ingredient is inflation. A zero-energy quantum fluctuation would normally exist for only an instant before collapsing back into the vacuum. But if the fluctuation contained within it an inflaton field capable of driving exponential expansion, it would inflate dramatically before it could collapse, stretching a microscopic quantum event into a macroscopic, persistent universe. The universe would then be self-sustaining, its expansion continuing long after the inflationary pulse that created it. This scenario does not fully resolve the mystery of origins because the quantum vacuum itself is governed by physical laws and possesses properties and potential. Whether this constitutes true nothingness or simply a different kind of something is a question that physics alone may not be equipped to answer. It ventures into territory where science and philosophy interweave in ways that are not always easily separated. But the idea that the universe's existence might follow from the same quantum principles that govern the behavior of atoms is remarkable in its implications. It suggests that existence does not require an external cause, that the universe might be, in a very deep sense, its own reason for being. Our place in the cosmic story step back from the details and allow the full arc of the story to come into focus. 14 billion years ago, from a state of extraordinary heat and density, an expansion began. In the first fraction of a second, the fundamental forces separated and particles came into being. In the first 3 minutes, nuclear reactions forged the lightest elements. After 380,000 years, atoms formed and light traveled freely for the first time, leaving behind the fossil radiation we call the CMB. After hundreds of millions of years of darkness, the first stars ignited, forging heavy elements and scattering them across space in spectacular deaths. Galaxies assembled, merged, and grew. Stars formed by the billions, many of them with planets in orbit. On at least one of those planets, around one of those stars, in one of those galaxies, chemistry reached a level of complexity that produced life, and eventually minds capable of tracing this entire history back to its source. You are made of atoms forged in stellar cores and scattered by stellar explosions. The carbon, nitrogen, oxygen, and iron in your body were synthesized in the nuclear furnaces of stars that lived and died before our sun was born. The hydrogen in your water is primordial, created in the first 3 minutes after the Big Bang, more than 13 billion years ago. You are, in the most literal physical sense, a product of the Big Bang. The observable universe contains hundreds of billions of galaxies. Each galaxy contains hundreds of billions of stars. Many of those stars host planets. The cosmos is unimaginably vast, and yet it all traces to a single event, a single set of initial conditions, a single moment when everything began. Understanding the Big Bang is not merely an academic exercise. It is humanity reaching back across the full span of time to reconstruct its own origins, to understand what kind of universe this is, why it has the properties it does, and how the staggeringly improbable fact of our own existence came to pass. The answer, as best as science can currently determine, is this. The universe began in a state of extreme density and temperature, perhaps emerging from quantum fluctuation, perhaps rebounding from a previous cosmic cycle, perhaps for reasons we do not yet understand. It expanded and cooled. Quantum fluctuations imprinted subtle variations on the early plasma. Inflation, if it occurred, amplified those variations and smoothed the overall geometry of space. The first atoms formed. The first stars ignited and died. Galaxies grew. Stars were born and died in their billions. And on a rocky planet orbiting an ordinary star, on an ordinary spiral arm of an ordinary galaxy, carbon-based chemistry assembled itself into beings that look up at the night sky and ask where all of this came from. The Big Bang was not an explosion in space. It was the beginning of space itself, the beginning of time, the beginning of the universe, and the beginning of the story that led to you. What we still do not know. Science is at its most honest when it acknowledges the boundaries of its knowledge, and in cosmology, those boundaries are both real and clearly marked. We do not know what caused the Big Bang. The initial singularity is a point where our equations break down, and whatever physics governed it lies beyond our current reach. We do not know whether inflation actually occurred, though the evidence for it is compelling. We do not know what the inflaton field was, or why it began inflating. We do not know the nature of dark matter, the substance that makes up more than a quarter of the universe's energy content. We do not know what dark energy is or why it has the particular value it does. We do not know whether the Big Bounce is real or whether our universe is part of an endless cycle. We do not know whether other universes exist, whether spawned by eternal inflation or produced by other mechanisms entirely. These are not small questions. They are among the deepest that the human mind has ever formulated. And each one of them is an active area of research pursued by thousands of scientists using telescopes, particle accelerators, gravitational wave detectors, and the most powerful mathematical tools ever developed. The cosmic microwave background continues to be studied with increasing precision. Future surveys of the large-scale structure of the universe will test cosmological models to new levels of accuracy. Gravitational wave observatories may one day detect primordial signals from inflation or from a Big Bounce. Particle accelerators probe energies approaching those of the very early universe, searching for dark matter candidates and signatures of physics beyond the standard model. The Big Bang is not a complete answer. It is the best answer we currently have, supported by more independent lines of evidence than perhaps any other theory in science. And the questions that remain beyond its reach are not signs of failure, but invitations. They are the universe's way of reminding us that the story is not over, that there are chapters still to be written, and that the universe has more surprises in store. The greatest adventure in the history of science is not finished. It has barely begun. Thank you for watching. If this journey through the origins of the universe left you with questions or thoughts you want to share, leave them in the comments below. And wherever in the world you are, whatever time it is there, take a moment tonight to look up at the sky. Every point of light you see is a chapter in the same story. You are part of it too.